Alrighty, 3.8, representing solutions. So, you need to be familiar with seeing drawings. I've said this a million times, but here's some representations of solutions specifically. So here we have a solution of some ions in some water. I also have here, we got hydronium and HF and F minus. Now, that is something we'll talk about more when we talk about acids and bases even more. For now, we'll just leave that at that. Okay, so we have some different types of solutions. So aqueous, I mentioned earlier, were dissolved in water. Water happens to be the solvent. This is the most common solution you're going to run into in chem. But again, there is different solvents as well, but this is a special one because we dissolve in water almost all the time. You have electrolytes. So electrolytes, as it says here, we generate electricity in a solution, okay? I'm actually going to talk about electrolytes with food in a second for those curious. Yeah. And so we have some kind of ions because the ions are the ones that are going to generate electricity for the electrons to move around. And so if I have a strong electrolyte, that means the thing is entirely made of ions up in there. If it is a weak one, we only have some ions, but we also have partly whatever other things that are in there. So we might have parts of the salt that aren't ions, and then parts of the salt that are ionized. If it's a non-electrolyte, then you are not going to conduct electricity. So sugar water, for example, does not conduct electricity because sugar is a covalent compound. What kinds of interactions do covalent compounds have? We have good old London dispersion or any other IMF depending on what kind of molecule. Yeah. All right. So, a list of things you need to memorize, unfortunately. So, you need to know your strong acids and your strong bases. I did not include a list on here for some reason, but I do have it on the website under Unit 3. So find the list of strong acids and strong bases for you to memorize. Okay. Now, we will talk about strong acids and strong bases some more later. For now, what you need to know is that they dissociate two ions completely. So, for example, if I had hydrochloric acid as a solid, and then I dissolved it in water, aka AQ, that means I have a whole bunch of hydrogen ions and a whole bunch of chloride ions in the solution. Okay, so that's what you need. So if you have a strong acid or a strong base, automatically in your head, you should know that they dissolve as their ion forms. Coolio. Again, this is going to be super duper important later on in Unit 8 when we talk about that stuff. But we are going to use the list of strong acids and strong bases in other units besides this one. So make sure you know your list and really memorize. Cool. Alrighty. So electrolytes. You've heard of them, I'm sure. You've heard of Gatorade, I'm positive, right? Amongst other kinds of electrolytes. Now, it's electricity, right? And so for example, your body, you have a whole bunch of cells. And in those cells, you have biochemical reactions happening to it. And so in those reactions, you need a lot of electricity for them to actually happen. You'll learn about this in cell bio or general bio, depends on college you. And so you have, for example, the nervous system in your body, which are the nerves connecting to your muscles and stuff. And so these nerves and muscles can contract, right? Because you got your muscles contracting from doing physical activity, for example. And so when you have your muscles contracting and whatnot, you need electricity for that. Now, do you actually need to drink electrolytes? That honestly depends on your diet and how much of an athlete you are. Technically, if you're not some super duper athlete, you don't really need to drink electrolytes. As long as you're just eating a nice balanced diet, then you probably are fine. And so the idea of needing Gatorade at a game, for example, like if you play football or tennis or whatever, it's honestly probably not. You don't need it unless your diet sucks. Then sure, drink something with electrolytes. But usually the general population does not need to drink electrolytes if their diet is fine. Okay. Other things electrolytes are used for, we balance our cells, the pH specifically. So we're trying to control the amount of hydrogen ion in our blood, for example, and amongst, your cells in general. And electrolytes can be good for hydration purposes as well. But again, the average person doesn't really need to drink electrolytes. You don't need the fancy water with electrolytes in it, but it's a good selling point because people don't know science. Again, if you're like a huge athlete, then it makes sense to, but if your diet is fine, you most likely don't need it. If you're cramping, it could help if you drink it fast enough. Yeah? Cool. Alrighty. So, visualizing solutions. We've talked about solution making in the previous section as well as in the previous unit, but you, again, need to be able to draw these out and mark what kind of interactions are happening. So, if you know you have a strong, weak, or non-electrolyte, then you know if you have charged ions or if you only have partially charged or you have no electrolytes at all. And so here, for example, you have a salt, in this case, the good old sodium chloride salt. And so you should be able to draw what kind of interactions are happening. So we have the NaNCl, we have our ionic bond, versus the IMFs of water to itself, the hydrogen bond. And then we have the IMF between the water and the ion. And so make sure you can put the specific interactions, whether it's an ionic bond or a specific IMF, make sure to label that in your drawing if the question asks. So that's for NaCl. Sugar water. Sugar is this molecule you could see right here. For example, sucrose is one of the sugars you can have. And so you have the interaction between this sugar and this water, and it's going to be an IMF. Now, it depends on what the formula is. Is there a dipole or not? You have to look carefully at that. In this drawing, you can't tell. I mean, I know because I know what sucrose is, but like if you are doing this on the test, you would most likely know what kind of formula this is or what it looks like with the Lewis diagram in order to determine what IMF it is. So just be very mindful of marking those in your drawing. Cool. So here's a quick FRQ. Read it to yourself, pause this video, and then I'll talk about it. Okay, so you have a couple options on what to do for B. Now, for part A, I gave you the answer because we haven't talked about how to get net ionic equations yet, because it's the next unit. So for now, I just gave you the answer. For part B, as it says here, the diagram below is incomplete, so we need to draw a species to accurately portray whatever we're trying to portray. And so we look at what's given in A. We have two options. We have our calcium ion, and then we have our carbonate ion. And so those are the two things that could be potentially missing in our drawing. And so if we go back to the original problem, I will move this so we can see. You can see that we are adding Na2CO3, okay? And so that means we have excess CaNO3 too. Okay? So, excuse me, sorry. So, we can see that in this we have a bunch of NO3 sticking around, but we have solid CaCO3 on the bottom. So that's where the excess part comes in, because it's literally on the bottom and it was in solution, so we have extra of that. So if I think about this a little bit more, I can again think about what solidified. We have the CaCO3, and so what thing is going to be the limiting reactant versus the excess reactant? So think about that for a second. Cool. So we have NO3 sticking around. We have Na sticking around. All of the carbonate is used in the... Oh gosh, I didn't just realize I put CO2 here instead of CO3. Oh my gosh. Ay, ay, ay. You know? Not proofreading. Anyway, so we are looking at who's excess and who's limiting. And so I see that the carbonate is going to be the limiting reactant. So the species that should be in here is our Ca ion. So I should put Ca plus 2 or Ca2 plus. Again, it really doesn't matter what order you're putting these in. So then you just draw a couple of them in there. Bam. Put them in a circle. Bam. Easy. Just be careful about what is being with what. If you're confused about why this is the answer, please ask. I can go over it more. I kind of breezed through it a little bit. So just ask. I will happily help you. Okay, so if you run into these things in the textbook, or if you're looking up studying material for this unit, there are a couple things you do not need. I did talk about some of these earlier, but not all of them. So we have the colligative properties. You don't need to worry about that. They do affect physical properties, but for this class, you don't need it, and you'll only need it if you are in specific STEM classes. So don't even trip about it for general chemistry of college. Molality, I said earlier, you don't need. You don't need percent by mass or percent by volume for solutions. Cool. Alrighty, here is an MCQ. So read the question, look at your answers, think about it, and then I'll talk about it in a few moments. Alrighty. So, best conductors we have to think about from the previous sections and a little bit of the previous unit. Who's good at conducting? So let's just go through each option. So NH3. NH3, we got IMFs in there, but molecules and IMFs don't really conduct well, so it can't be A. We look at C. I do have some ions in here, so those can conduct. B, I have a lot of ions in here, so that can really conduct. And then D, we have a molecule. Molecules don't conduct because they're just IMFs. They don't hold a full charge. They only hold partial charges at the most. So my options are B or C, but the best conductor has more ions, so therefore it's going to be B. Cool. Alrighty. Here's 2 your turns. They are drawings. Try it out, and then I'll go over the answers in a few moments. Okay, so for number 1, it honestly depends on how you want to draw it. It is definitely going to be some kind of IMF because we have ammonia and water, and those are both molecules. So you can draw this, in different ways. Since it's a diagram, I'm going to just use circles. Circles are easy. I will do filled in N versus, so this is going to be N, and then H is going to be like a, no, let's make it a triangle. And then oxygen will be a circle because it's easy. And so our NH3, we got our little dot. Then we got 3 triangles sticking out. Boom, boom, boom. And so then I can have water. So water is chilling over here with our oxygen and our, oops, wrong one. Triangle, triangle. And so I can draw an interaction between them. So the hydrogen can interact with the oxygen like so. And that is an IMF. Let's think about what kind of IMF this is. So NH3, if I think about the Lewis diagram, is going to look like this. So we have a trigonal pyramid and we have polar bonds. So therefore, this is going to be a polar molecule. Then we have water. And so water is also a polar molecule. So we have a DDI. Cool. Or actually, do we have a specific DDI? N bonded with H, O bonded with H. Ah, we got hydrogen bonds. So the stronger DDI. Because we have hydrogens bonded to either N, O, or F. So in this case here, and then here. So those are good polar bonds. And so that's going to be an H bond. So we got the general. Our general is just IMF. And then we can get more specific with DDI and then even more specific with hydrogen bonds. Yeah. Cool. Alrighty. Draw a diagram that correctly depicts the solvation process of MgCl2. Show interactions. Okay. So I'm kind of lazy to do this. So I'll just show the picture from earlier. Oh no, it's in the other. Oh, it's in the other section. Dang it. Do I want to open it? No, I'm lazy. Okay, we'll just do it. It's fine. It's fine. Okay. So we have our solvation of MgCl2. So I can show we have a solid of that. And so, oh, this is a terrible drawing. You should draw a key and make it more obvious which one is which. So my Mg is going to be the smaller one, Mg plus 2. And then Cl minus 1 is going to be the bigger guy. Draw it better than me. And so we have that versus the water. I'm going to put water over here. So we're going to make water just like that. Cool. Then we got our little hydrogen bond over there. We have our ionic bonds here. So they're going to break apart so we can have our small guys and our big guys. And then here, our IMFs are breaking. And I could draw more if I wanted to. And then they are going to smoosh together in a solution. And so if this is the chloride ion, then I have to think which partial side do I need. I need my partial positives, which is the hydrogen side. And so the hydrogen side would face towards the chloride ion. Like that, kind of. And then the magnesium positive is going to hang out with the partial negative of water. Kind of like that. Oh, these are so bad. But yeah, show the drawings to the best of your abilities. Cool. I think that's it. Yep, that's it for this section. Okay, bye.